Okay, so welcome to your exam review for ADM2303. My name is Andrew. We've gone through that. So let's dive right into our first question. So here is your first question. I will give you a couple minutes to try this question on your own, and then we will take it up together. Okay, so that's been about 3 minutes. So let's go ahead and just start. So first, we can read the question. So, after increased patrol, cars on the road travel at speeds averaging 55 kilometers an hour. If 93% of the vehicles travel below 68 kilometers an hour, what approximate standard deviation could represent this model, assuming a normal model is appropriate? So, let's say you got this question on an exam and you had run out of time, or you really had absolutely no idea how you might solve a problem like this. Well, the first thing that you can do is you can eliminate E. E will never be the right answer in this particular question. And I say that E won't be the right answer because of this negative sign. Okay. Our standard deviation will never be negative. So that's our first indicator there, is that because of this negative standard deviation, we know we can cross out E. From there, we have to think about this a little bit conceptually. So, importantly, our question tells us the following, right? Assuming a normal model is appropriate. So, let's go ahead and just draw our normal distribution, right? So, we have our function of x along our y-axis, and we have something that looks approximately normal, right? Standard normal curve, so we're centered around 0. We don't have to have a standard normal curve though. So in this case, let's not center it around 0. Let's, in this case, center it around our mean, right? Our normal distribution is centered around our mean, or our x bar, which in this case, x bar is equal to 55 kilometers per hour, right? What the question tells us is that 93% of vehicles travel below 68 kilometers an hour. So if we were to write this here, 68 kilometers an hour, what that means is that 98% of the traffic is to the left of this value, right? So to the left, 0.98. Okay, so this gives us some important information, because what do we know with our z-score is that we can go z is equal to the observed value of x minus the expected value of x divided by our standard deviation of x. Well, in this question, of course, what we don't know is we don't know our standard deviation of x, but we do know our observed value of x, which is 68, and our expected value of x, which is 55. We also can derive a z-score. So knowing that 98% of our observations fall to the left of 68 kilometers an hour, we'll just go to our standard normal curve here, and we'll look up 0.98, and we get 0.98, which is right here. Somewhere between 2.05 and 2.06. Oh, sorry, it's not, I made a goof here, I think. It's not 98%. My apologies, everybody. It's not 98%. That's embarrassing. The question told us that it was 93% of vehicles, right? 0.93. So in this case, what we're going to do is we're going to look up 0.93. So 0.93 is right here. Go back to our question, right? We get our standard normal curve here of 1.47 or 1.48. So thereby, we could just solve and we say it's halfway between 1.47 and 1.48. Now, there are more advanced ways you can calculate that number, but you can also just approximate it as halfway. In this particular question, if you pick 1.47 or 1.48, it's not going to change your answer. So we sub in our value for Z. So Z 1.475 is equal to 68 minus 55 divided by our standard deviation. We then rearrange to solve for our standard deviation, to which we then get our standard deviation of X to be 8.81, right? Effectively, if we were to draw our normal distribution centered around 0, what we said was that this value that we looked up in the Z table was 1.475, and the area to the left was equal to 0.93, right? The area to the left, 0.93. So there we have it. That's how we would solve for this question. Now, I apologize for making the mistake about 0.98. I hope that didn't confuse you. And if you see me making a silly mistake like that again, please just chime in the chat and let me know that I've just read the question wrong. That would be helpful. Are there any questions on that question? Okay. Let's go to our next question. I'll give you a few minutes. We'll go from there. Okay. So the 2012-2013 NHL lockout was a labor dispute that took place on September 15th, 2012. The owners of the league's franchises declared a lockout after members of the National Hockey League NHLPA after a new agreement could not be reached. The lockout shortened the 2012-2013 NHL season from 82 to 48 games, and many Canadians and hockey fans alike were expressing frustration. Angus Reid conducted a survey of 1,508 adult Canadians, finding that 36% of respondents believed that the owners deserved most of the blame for the lockout. Then we're asked the following question. Suppose that in fact, for the whole population of Canada, 33% of adults believe that owners deserve most of the blame. What is the probability that a survey of 1,508 Canadian adults would have found the proportion believing owners deserve most of the blame to be 0.36 or 36% or higher? Okay. So I'm going to show you the solution, but don't get too distracted by that just yet. Let's go through what we need to check. And really what we have to check is, can we apply a normal distribution? So we want to think about, well, is there a random sample? Is it random, independence, n times p and n times q both greater than or equal to 10? And in this case, well, we'll assume that there was a random sampling. We'll assume then that there's independence. At n times p, if we said that p is equal to 0.33, which is the population, the average of our population, and we have 1,508 Canadians, that's given to us right here. So 1,508 times 0.33 is going to be greater than or equal to 10. And likewise, then Q is equal to 1 minus P, which is equal to 0.67. And 1,508 times Q, 0.67, is also greater than or equal to 10. So both greater than or equal to 10. And we have our 10% condition, 10% of the population. And this is really less than 10% of the population. Well, 1,508 Canadians is certainly less than 10% of the population of Canadians. So we will also go ahead and check that off. So From there, we think that we can apply a normal distribution. So let's just visualize it. So we'll draw our standard normal curve looking like this. We'll center it around our mean of 0.33. And then we have our observed value, which is 0.36. Whoops. .36. My iPad is not working well today. 0.36. And what we're asked is, what is the proportion of owners deserve most of the blame to be 36% or higher? So in this case, we're looking for the area to the right. So if we just focus our attention right here on our Z-score, what do we notice? Well, we have the p hat, that's the proportion of our sample that's given to us to be 0.36 minus our expected proportion, that's 0.33. And what we don't have is the standard deviation of the proportion of our sample to calculate our Z-score. So we need to go ahead and calculate our standard deviation of p hat. So that's where we'll focus our standard deviation of p hat, which is right here. Standard deviation of p hat is equal to the square root of p times 1 minus p divided by n. Or otherwise known as equals the square root of p times q divided by n. So we go ahead and we do that math, and what we get is a standard deviation of the proportion of our sample to be 0.0121. Then we go ahead and plug that standard deviation into our Z-score, and we calculate our Z-score, and what we get, we draw our standard normal curve now, we get a Z-score here of 2.48. And again, we're looking for the area to the right. So to that extent, we would then go and look this value up in our Z table. So 2.48 is what we're looking for. So 2.48 is right here. .99343. I've rounded to 4 decimal points, so 1 minus 0.9934 will give us the probability that Z is greater than or equal to 2.48 to be 0.0066. Consequently, what we would say is that it's not very likely that a survey of 1,508 Canadians would find the proportion of people believing that owners deserve most of the blame to be 36% or higher. That's not a very likely outcome of that survey. Okay, so having looked at this question, now the same basic introduction applies. But now let's look at player salaries. Okay, so following this lockout, more Canadians became interested in knowing how well NHL players get paid, especially those playing well. An online article indicates that a good player should receive an average of $6.6 million with a standard deviation of $2.1 million. Assuming that a good player should have a good points per game score, you randomly sample 40 players with high points per game scores and find that the average of their salaries is $5.6 million. What is the probability of a random sample of 40 good players, that is, those referred to in the online article that's described right here, would have an average of $5.6 million or lower? Okay, well, we can go ahead and solve for this question. So again, before we look at our solution, let's just draw our normal curve here, because we're going to assume that there's a normal distribution here. So we are told that there's a mean of $6.6 million, 6.6, and this is in millions of dollars. And what we're told is that the random sample had a mean of 5.6 million. And our question is asking us, what is the probability that a random sample of 40 good players would have an average of 5.6 million or lower? That is our area to the left. So we can look at this and said, well, we can calculate our Z score. So Z is equal to the observed value of Y minus the expected value of Y divided by the standard deviation of the mean of our sample. In this case, we do not know the standard deviation of the mean of our sample. So we are going to go ahead and calculate that. So the standard deviation of Y bar is equal to sigma. That's this Greek letter right here. This just represents the standard deviation of your population, which of course is given to us in our question. So our standard deviation of our population divided by the square root of our sample size. When we do 2.1 million divided by the square root of 40, we get $0.3320 million. Now, if it were me, I would just leave these units the way they are. You can make sense of it later, but I wouldn't put a bunch of zeros, but you can if you want. So 2.1 million divided by the square root of 40 gives us standard deviation of Y bar to be 0.3320. And that, of course, is in millions of dollars. Remembering that when we have a standard deviation, we need to remember what units it's in, right? So in this case, we're in dollars, and that is millions of dollars. From there, we can go ahead and calculate our Z score. So Y bar minus mu, or the mean of our population, divided by the standard deviation of Y bar. So we get 5.6 million minus 6.6 million divided by 0.3320. This, of course, gives us a Z score of negative 3.01. And we can go ahead and look that up in our Z table if we want. Negative 3.01. That's going to be right here. And that's the area to the left. And we can round to 4 decimal points. So that's just going to be 0.0013, right? Meaning that the probability that it's in this tail is equal to 0.0013. If you wanted to ask a question, then this isn't in this question, but if you wanted to ask, what is the probability that they make $5.6 million or more? So the probability that Z is greater than or equal to negative 3.01 would just be equal to 1 minus the probability that Z is less than or equal to negative 3.01, which is equal to 1 minus 0.0013. 1 minus 0.0013 gives us 0.997, right? So that is the probability that it's greater than in that case. But of course, the question is asking us, what is the probability that it's $5.6 million or lower? So this would be our final answer right here. Okay. Now moving on. The beginning part of this question all has stayed the same. There's nothing new about the first paragraph of that. The new part is part B. So I'll give you a chance to read part B, and then we'll take it up together. Okay. So if you're given a question like this is kind of a concept understanding question. And this is where it is important that you check your assumptions and conditions for your normal distribution with almost every question where you rely on the normal distribution. So in this question, they tell us that the author considers good players to be only 300. Unlike A, the question we just did, where we assumed that there was many more. So importantly, when we look at this, we can assume that the players are independent. We can assume that there's a random sample. We can assume that there's enough quote unquote success and failures, and we can assume that the sample is sufficiently large to use a normal distribution. However, the condition that is not met here is that we have a sample that is greater than 10% of our population. And to use a normal distribution, you have to have a sample size that's less than 10% of your population. Now, most often, kind of in kind of survey statistics and kind of the real world, is you don't usually have to worry about the 10% condition. It's something that we kind of just check off and say, yeah, it's less than 10% of our population, because usually we're dealing with a survey of Canadians that, even if it was 10,000, would still be less than 10% of the Canadian population. In this case, the question tells us that we're dealing with a very small number of actually quote unquote good players. So uh, if we take a random sample of 40 good players to find out what their salary is, actually this becomes a bit problematic because it's greater than 10% of our population. So all we have to do in this case is we have to apply what's called our finite population correction factor. And perhaps you've seen this before. It's called the FPCF. That's the abbreviation. And what we do with the finite population correction factor is we apply it to our standard deviation of our mean of our sample. And that's all we do. That's the only thing we do to it. So we just calculate the standard deviation of y bar just like we would, and just like we did in part A of this question. So that is sigma, the standard deviation of our population, divided by the square root of n. And then we multiply it by the finite population correction factor. In this case, this is big N. That's the size of your population minus little n, which is the size of your sample, divided by big N minus 1. Okay, so if we look at this in the next line, it's simply the square root of 300 minus 40 divided by 300 minus 1. Okay, and we take the square root of that quotient and then multiply it by our standard equation to calculate the mean of our sample, or sorry, the standard deviation of the mean of our sample. Be very careful punching this into your calculator, okay? Specifically, this finite population correction factor, especially this equation right here, because if you punch it into your calculator without brackets, it's going to follow the order of operations first. So you're going to get something like 300 minus 40 divided by 300 minus 1, and that is not the correct answer. So just be very careful how you punch this into your calculator. But it's really quite straightforward once you pay attention to that. So now that we have our revised standard deviation to be the standard deviation of the mean of our sample to be 0.30963, if we just go back to the previous question, remember that we had 0.33. So our standard deviation got a little bit smaller there. And all we're going to do is calculate our z-score. So in this case, we get a smaller z-score. So the probability that z is less than or equal to negative 3.23 is equal to 0.0006. Whereas in part A of this question, where we assumed that it was less than 10% of the population, we still had a very small probability, but it is a much smaller probability when we consider the finite size of the population. Okay, that's a tricky one for sure. If you got that while you're listening at home, well done. That's awesome. If you didn't, this would be kind of an advanced type of question. And if it were me on an exam, I would probably, and I didn't know, I would probably move on. I'd probably do A and then move on and come back to this at the end and try and figure out if I can put together a reasonable answer. Are there questions about that? Okay. Okay, let's go to this question. I won't give you as long on this one because this one isn't as challenging. So I'll give you a minute or a minute and a half. Okay, so a certain type of tomato seed germinates 90% of the time. A backyard farmer plants 25 seeds. What is the probability that exactly 21 seeds germinate? Well, in this particular question, we're dealing with kind of a go, no go, grow, no grow kind of situation. And we're asked, what is the probability that exactly 21 seeds germinate? In this case, we should be cueing ourselves and thinking about that we're looking for a discrete probability distribution. And in this particular situation, that discrete probability distribution of choice would be what? Well, the answer, our binomial distribution. Okay, so we remember our binomial distribution. So our function of x, you may see this written other ways. You may see this written as the probability that x is equal to x, and so on and so forth. The function of x is still the same thing. F of 21 is equal to n factorial, where n is our sample size, so 25, divided by x factorial. That's our number of successes. In this case, it's 21 factorial times n minus x factorial times p. That's the probability of success, which we're given in our question to be 0.9 to the power of x. That's our number of successes, times q to the power of n minus x. And we remember that q is equal to 1 minus p. So 1 minus 0.90 is equal to 0.10. So we go ahead and we punch this all in our calculator. And what do we get? Well, we get an answer here of 0.1384. Now, this is absolutely a type of solution that you might see on an exam where they're not giving you the exact answer, they're giving you a range of answers. And this is kind of designed intentionally to frustrate students so that you cannot reverse engineer problems like this, where you kind of have to get an answer and commit to it. So in this case, the correct answer would be D, between 0.05 and 0.20. And to answer the question in the chat, yes, I'm recording this. It may take a while before it gets put online. So if you have questions, probably the best time to ask the questions is now, but I will put it online eventually so that you can look back on it. Okay. So then, a continuation of this question. What is the probability that fewer than 23 seeds germinate? Okay. So we won't spend too long here because this is content that was covered before your midterm, and I think you're likely quite strong on it. But so same type of question, but what is the probability that 23 or fewer, that fewer than 23 seeds, so less than 23 seeds, germinate? So there's a long way and a short way to answer this question. And if you took the long way, you're going to be doing this for at least 10 minutes. And the likelihood that you make a mistake is quite large. So what we have to calculate then is the probability that x is less than 23. So all we're going to do is 1 minus the probability that x is equal to 25 minus the probability that x is equal to 24 minus the probability that x is equal to 23. Unfortunately, there's no better way of doing this. You kind of have to do this by brute force calculation. So we first calculate the probability that 25 seeds germinate, that 24 seeds germinate, and 23 seeds germinate. And then we add that together, and we finally get a final probability here to be the probability that x is less than 23 to be 0.46257. Okay. Oftentimes students will say, well, Andrew, can I write it like this? The probability x is less than 23 is equal to 1 minus the probability that x is greater than 23, greater than or equal to 23. And the answer is, of course, yes. It will give you the exact same answer. Okay. This is really quick. So really, I'm giving you 20 seconds right? This is an easy mark on your exam that I hope you would get. What is the expected number of seeds that germinate? If you get this question on an exam, just be thankful, take the point and move on, right? Recall to calculate the expected value of a binomial is equal to n times p. So your expected value is equal to 25 times 0.9, which is 22.5, which then is your answer C, between 21 and 22.9. I'd say the most challenging part about these set of three questions is not necessarily the calculations and more so the ranges that are given. For whatever reason, it appears that students often struggle with these ranges. Um, Perhaps it may be a bit of panic in exams of trying to get the question done and move on, and you just want to get the final answer. And this isn't really a final answer. It kind of feels incomplete because you're just saying, well, it's somewhere between this range. Of course, you've calculated what it is, but you're not filling in the bubble. So it appears to be a bit of a sometimes trips students up a little bit. Okay, here's another conceptual question for you. So I'll give you 45 seconds. Okay, here's our 45 seconds. So a hobby farmer plants 200 seeds. We would like to know the probability that greater than 179 seeds and less than 186 seeds germinate. Can this question be answered using the normal distribution? Well, in this case, we're looking for the most right answer. And the most right answer here is that yes, because n times p and n times q are both larger than 10. And I've proven that over here in the margins for us. So 200 times 0.9 gives us 180, and 200 times 0.1 gives us 20. Both are greater than or equal to 10. So that meets one of our conditions for a normal distribution. Some of the other assumptions for our normal distribution, we have to assume that the seeds are independent of each other, that they are random, that the sample size is large enough, and that it's not greater than 10% of the population of seeds. Well, in this case, we're going to assume that 200 is not greater than 10% of the seeds in the world, so we are fine with that. We'll assume that they're just random and independent seeds, that there's no reason to believe that there's a bad group of seeds. So in this question, really, the most right answer is B. A is not right because there are conditions where you might not be able to use the normal distribution, right? If they weren't independent, or if they weren't random, or if the sample size wasn't large enough. These would be all reasons why you might reject using a normal condition assumption. So A is not right. You cannot always use a normal distribution. B is right. We've covered that. C is factually incorrect uh, because no n times p are larger than 10. This is actually a condition that you need for the normal distribution. A sample size of 200 is generally large enough. So in this case, this is also not the right answer. And E, if you could find a reason why E was the would be appropriate. So if n times p and n times q weren't greater than or equal to 10, perhaps this would be a situation where you cannot use a normal distribution. But of course, that's not the case. So again, this is also wrong. So B is the most right answer in this case. So again, these types of questions, when I was a student, I also struggled with because selecting the most right answer can be challenging. I know that, but you really can't overthink this question too much and just select the most right answer. Okay, here's our next question. So I'll give you, 2 minutes or so, and then we'll take it up together. Okay. So if the life of a newly developed LED bulb has an unknown distribution with an assumed mean of 20,000 hours and a standard deviation of 2,500 hours, if a sample of 100 LED bulbs is taken, what is the probability that the mean life will be less than 19,500 hours? Okay, well, in this problem, we are going to look if we can use our normal distribution, right? So again, we're going to look, is the sample size independent? Is 100 sufficiently large? We assume a random sample. We say that 100 is less than 10% of the population of LED lights, which is a reasonable assumption, and that we assume the sample size is sufficient for at least 10 successes and 10 failures. These are all the assumptions that we kind of have to make. And the trick with this question is really that you have to kind of work through these assumptions and say, yeah, these are likely reasonable enough for me to assume a normal distribution, even though the question tells us that the distribution is unknown. Uh, I mean, for the sake of this course, really, I think you'd have to use a normal distribution to solve it. So um, you might be able to use a different distribution, but we won't get into that. So let's go ahead and we'll just calculate this. So what is the probability that the mean life is less than 19,500 hours? We can visualize this in our normal curve. I find it always helpful to draw out our normal curve. So in this case, we're told that the population mean is 20,000 hours, and we have a sample mean here of 19,500 hours. And we're saying that what is the probability that it's less than this? So we calculate the standard deviation of the mean of X bar, or the mean of our sample. So this is just equal to the standard deviation of our population divided by the square root of n. Just like we've done before in other questions, we get a z-score of -2. We look up -2 in our standard normal curve. We observe that this is the area to the left. So, of course, that is all we need. So there is our final answer. We can round to 4 decimal points, and we get B as our final answer. Okay. I think we've done a lot of questions like that. So let's just skip over these because we've done a lot of these. So this next series of questions is difficult. So I admit that they're difficult. So take your time, work through it, and we'll take them up together. So I'll give you a couple minutes to try this first question on your own, and then we'll do a different question, and then we'll keep building on it. Okay. So the Himalayas and adjacent mountain ranges are the source of several major rivers. The water in the rivers comes from two sources, rainfall and glacial melt water. Rainfall varies from year to year, and the coefficient of variation. And they nicely give us what that means. The COV is equal to the standard deviation divided by the mean of rainfall in the basins of the four largest rivers are the Ganges, 0.12, Brahmaputra, 0.11, Indus, 0.40, and the Aral river basin to be 0.29. By contrast, glacial melt water has a coefficient of variation of only 0.04 in each of the four river basins. Assume the amount of rainfall and glacial melt water are normally distributed. So then the first question we're asked to deal with here is, what is the probability of rainfall in the Aral River Basin being less than 40% below average? This is a tricky problem, okay? And the important part you need to kind of recognize in this question is that because we are just dealing with the Aral River Basin in this particular scenario, 40% below average, it honestly doesn't matter what size of expected value we pick. We could pick 10 millimeters of rain, we could pick 100 millimeters of rain, we could pick 1,000 millimeters of rain, but because it's normally distributed around our mean, whatever value we pick here, which is X bar times 0.6, right? 40% below X bar times 0.6, it will always be 40% below. Now, given we have the coefficient of variation for the Arrow River Basin, and that's given to us in our question. And that tells us the measure of standard deviation relative to the expected value. Because we have this value, we can assume any value for our expected value, and our standard deviation will be scaled accordingly. Okay, so you can try this question on your own to try different values. You could put in 10, you could put in 50, you could put in 100, you could put in 1,000. But at the end of the day, you're always going to get to the same Z score. So really what we're asking is, what is the probability that is 40% below average? So we're looking for a Z score in this case. So if we assume a mean of 100, 40% below 100 is just 100 times 0.6, or if we want, we could say it's 100 times 1 minus 0.40, which gives us 100 times 0.6, which gives us 60. And from there, we can go ahead and calculate our Z score. So 60 minus 100 divided by our standard deviation that we calculated right here in this step, where we took the coefficient of variation is equal to the standard deviation divided by the expected value. So in this case, we rearrange to solve for our standard deviation. So if we assume 100 millimeters of rain times 0.29, then our standard deviation will be 29. No question, this is a challenging question. Most students likely would answer A. That would be probably the most common answer on an exam. This is, of course, not the right answer. This is the wrong answer. But in this case, we then look up negative 1.38 on our Z table. So the probability that Z is less than or equal to negative 1.38 is equal to 0.08379. So our correct answer here is B. No question is challenging. Okay, let's go to the next question. So the beginning part, the first paragraph, has all stayed the same. The only thing that's new here is the question itself. That's the only part that's new. Okay. I won't leave you too long on this question because I do know how hard it is. So which river basin has the highest probability of rainfall less than 1.3 standard deviations below average, right? Critically to this question is acknowledging this part right here, normally distributed. So if we draw 4 normal distributions, right, we'll say that this is Aral, Ganges, Brahmaputra, and Indus. And all of them are normally distributed. So all centered around 0. And they all are 1.3 standard deviations below 0. So this would be negative 1.3, negative 1.3, negative 1.3, negative 1.3. To that end, if we were to look up a Z score, we were to look up the probability that Z is less than or equal to negative 1.30, you would get the same probability for each one of these river basins. Okay, so the key here is recognizing that negative 1.3 standard deviations below the mean is the same across all of these normally distributed variables. In this case, the variables are the river basins. So the probability is the same for each river. Okay, one more challenging question, and then we will go do some other types of questions, but I think that these are the most challenging in this review. So again, this part has all stayed the same. The new part is that second paragraph. I will give you a few minutes to try it on your own, and then we'll take it up together. Okay. I don't necessarily think that you're likely done this question, but let's go ahead and just work our way through it for the sake of time. So I'm not going to reread the whole question. I'll read the second bit of this question. So in the Indus River Basin, the average rainfall is 396 millimeters. The average glacial meltwater is 10.6 millimeters. What is the coefficient of variation of the total rainfall plus glacial meltwater in the Indus River Basin, assuming a correlation coefficient of 0.54 between rainfall and glacial meltwater? You can use the other information in Asia's glaciers if you need it. Now, a couple concepts that we can just explore just kind of off the start. So if we have kind of an X and Y plane, we can say that perhaps it's rainfall and glacial meltwater, and then we have kind of these points that maybe look something like this. Now, our question tells us that there's a correlation coefficient of 0.54. Now, we remember that a correlation coefficient is also written as R is equal to 0.54. And what that means is that we have a modestly strong positive linear relationship between rainfall and glacial meltwater. In other words, as the amount of rainfall increases, so does the glacial melt. So as glacial melt increases, so does rainfall, and vice versa. So that's just kind of an overview of what the correlation coefficient means. But in this case, we are given a question and we're asked, well, what is the coefficient of variation, the coefficient of variation of rainfall and glacial meltwater? So we need the standard deviation of rain plus glacial divided by the expected value of rain plus glacial. Okay? This is really just combining two random variables. In this case, our random variables are rainfall and glacial meltwater. So it is possible to calculate our standard deviation of each of these variables. And importantly, we are given our expected values of both rainfall and glacial melt. So our expected value for rainfall is 396, and our average glacial melt is 10.6 millimeters. We are also given the coefficients of variation. So we're given the coefficient of variation of 0.40 from the Indus, and we're told that glacial melt has a coefficient of variation of 0.04. So we're given this information so we can solve for our standard deviation of rainfall and our standard deviation of glacial melt. Truly, I probably should have been less lazy here, and I probably should have said the standard deviation of rainfall is equal to 158.4, and the standard deviation of glacial melt is equal to 0.0424, right? Sorry, 0.424, right? Truly, as long as you can keep these variables understood in your head, it doesn't really matter if you use two variables of x. If you were modeling, it would, but in this case, we're not, so it doesn't really matter. So before we get focused on what's happening on the right, so before we focus on this, let's just focus on what is happening here on the left. So let's first calculate our expected value of rain plus glacial. In this case, the expected value of rain plus the expected value of glacial is equal to 406.6 millimeters, right? You'll remember this from your course, the expected value of x plus or minus y is simply equal to the expected value of x plus or minus the expected value of y. In this case, the expected value of x plus y is equal to the expected value of x plus the expected value of y. This is exactly what we did right here to find the expected value. So now that we have the expected value, we have to find our standard deviation of our rain plus glacial. Now, we have to account for the fact that we have a positive correlation coefficient right here. So we have to account for that. So first we're going to calculate our variance. So our variance of rain plus glacial is equal to the standard deviation of rain squared plus the standard deviation of glacial squared plus 2 times our correlation coefficient. That's R times the standard deviation of rain times the standard deviation of glacial. We get our standard deviations from what we calculated on the previous slide, our standard deviations of both rainfall and glacial melt we calculated here. We can sub those values into our equation, to which we get our variance of rain plus glacial melt to be 25,163.27. And this is going to be in millimeters squared, which doesn't make any sense. So we're not going to worry about the units too much. From there, we can take the square root of our variance. So the square root of 25,163.27 millimeters squared will give us the standard deviation of rain plus glacial of 158.63 millimeters. From there, our coefficient of variation is just equal to our standard deviation divided by our expected value. So now we sub these values in and we get a coefficient of variation to be 0.39. It's really important when we're doing a question like this, when you're dealing with a correlation coefficient and you are trying to calculate the standard deviation and the variance, that we are mindful of the sign of the correlation coefficient. So in this case, we have R is equal to positive 0.54. So we don't have to be too mindful of it. Our equation isn't going to change. Now, if, and this is just a hypothetical if, because this is no longer part of the question, but if we had rainfall and glacial, and instead of a positive correlation coefficient, we had a negative correlation coefficient, right? Something that looked like that. In that case, we'd have R is equal to negative, let's just say 0.54, in which case we would have to sub in negative 0.54 in for R, which then would result in this, instead of being positive, being minus. Okay? We have to be mindful of the sign on our correlation coefficient. Okay, in this case, we're dealing with a positive correlation coefficient, so it doesn't affect our answer. But if it was a negative correlation coefficient, it would affect our equation and our ultimate answer. Okay, again, this is a very challenging question. There's no doubt in my mind that this is a challenging question. I wouldn't expect the vast majority of students to necessarily answer this correctly, but hopefully, given that you are here and have seen now a question like this, when you go and practice some more questions, you'll become quite familiar with it. Okay, let's go to this problem here. So there's a number of questions here, so I will give you some time to work through this, and then we will take it up together. Okay, so the company Innova manufactures small gasoline engines in 3 factories, that is factory M1, M2, and M3. The engines are tested before delivery and are declared to be acceptable, defective, minor, defects that are repairable, or unacceptable, that is major issues that are not repairable. The following table provides the number of engines for each category of production for the 3 factories. Okay, so what is the probability? Before we get there, let's just take a look at what else the question gives us. So the question nicely gives us what we call a contingency table. So this is likely familiar to you, or at least hopefully. And we remember that with a contingency table, we're dealing with two categorical variables. In this case, we're dealing with a categorical variable that is factory, and we're dealing with a categorical variable that is engine status. So it's either acceptable, defective, or unacceptable. In our contingency tables, we notice that we have a total box here where both totals meet of 1400. And we remember that the sum of our rows, so 1155 plus 160 plus 85, is going to equal 1400, and 540 plus 380 plus 480 will also equal 1400. We remember that 450 plus 60 plus 30 is going to equal 540. And we remember that 60 plus 40 plus 60 is going to equal 160. So if you were given a contingency table that is incomplete, you could absolutely use the information in the table given to you to fill in the blanks if that was necessary. So let's get to our question. So what is the probability that an engine is defective or that it comes from factory M2? Okay, well, you'll remember this from your course. The probability of A or B is equal to the probability of A plus the probability of B plus the minus the probability of A and B, right? So in this case, we have our little Venn diagram here. These are non-disjoint. That's either going to be defective or M2, but then there's this instance in the middle, which is our joint probability, where it is both defective and from factory M2. In that case, this is called our joint distribution. Remembering that the distributions that are found in our margins are called our marginal distributions, and the distributions found within the body of our table are called our joint distributions. So all we do here is the probability of D or M2 is simply equal to simply equal to 160 over 140 plus 380 over 140 minus our joint distribution, which would be 40 over 1400, which gives us 500 over 1400, or 0.3571. What is the probability that an engine is defective and unacceptable? Well, in this case, they are disjoint events. They cannot happen at the same time, right? They cannot be both defective and unacceptable at the same time. So the probability that they occur at the same time, that being probability of defective and unacceptable, is equal to 0. Knowing that an engine was produced by factory M3, what is the probability that it is defective? Okay, this is a hint. Anytime you see something that's like knowing or given, that is our kind of our signal for our conditional probability going way back to the beginning of the course. And we refer to our conditional probability as the following, just looking at this general question first, or general solution first. So the probability of A given B is equal to the probability of A and B together divided by the probability of B. The nice thing about conditional probability is that which is our given is going to be in our denominator. Okay? So the probability of defective given factory M3 is simply equal to the probability that is defective given factory M3, which is 60. Oh, sorry, that's M1. 60 over 1400 divided by the probability that is factory M3, which is 480 over 1400. You could simplify this and put it as 60 over 480, and you would get exactly the same answer. And the answer is 0.125. So we could also say that that's equal to that. So knowing that the events are disjoint, what is the probability that an engine is manufactured at M1 or M2? Right? These events are disjoint. They do not happen at the same time. Right? It's either M1, M2, or M3, but engines aren't produced at the same time um, in different facilities. So what we're saying is the probability of A or B. So the probability of A plus the probability of B. So the probability of M1 or M2 is equal to 540. That's the probability of M1 over 1400 plus 380 over 1400, which gives us 920 over 1400 or 0.6571. Now that's one way to solve this. The other way to solve this would be the probability of M1 or M2 is simply equal to 1 minus the probability that it's M3, which is equal to 1 minus 480 over 1400, which will give us, roughly 0. Well, I'll just do it. 1 minus 480 divided by 1400, which gives us um, sure. So you could just do 1 minus that value and you would get, so 480 divided by 1400 gives us 0.34. So 1 minus that would give us 0.6571. So that's exactly that value. Okay, so let me just finish up solving these questions and then we'll go to some other content. So what is the probability that it's produced by factory M1 given it's unacceptable? So the probability of M1 and unacceptable divided by the probability that it's unacceptable gives us 30 divided by 1400 divided by 85 divided by 1400, which is just simply 30 divided by 85, which gives us 0.3529. And then finally, what is the probability that an engine is unacceptable and that it was manufactured at either M1 or M2? This is a bit challenging because really what it's saying is the probability of unacceptable and M1 or M2. So the probability of unacceptable and M1 plus the probability of unacceptable and M2 gives us 55 over 1400, which gives us 0.039286. Okay, so we've done this. So let's, we won't do Bayes' theorem. We don't need to do Poisson distribution. So let's look at a question like this. Okay. So the indoor pool at the local YMCA uses a filtration system to keep the pool water clean. The system requires that the filter be backwashed when discharge pressure for the water pump reaches 25 psi. The average time between backwashing is 10 days, and this time period follows an exponential probability distribution. And we're asked, what's the standard deviation of the time between backwashing? And then what is the probability that the next backwash will occur between 6 and 9 days from the prior backwash? So we're told that on average, there's one backwash every 10 days. Now, this isn't necessarily super useful. So the expected time then is just equal to our standard deviation. In this case, the expected standard deviation is equal to our expected backwash. So it's 10 days. That's how an exponential distribution works. But what is interesting then is what is the probability that the next backwash will occur between 6 and 9 days from the prior backwash? In this case, we have to get our value of lambda into a per day rate. because we're saying that it's one backwash every 10 days. But in this case, we're dealing with different units. So we're dealing with 6 and 9 days. We're dealing with individual days. So we have to get our lambda, that's our rate, into a per day basis. So one backwash divided by 10 days would be a rate of 0.1 backwashes per day. Now, when we're dealing with an exponential probability distribution, before we look at this solution, let's just envision it for a second. So our exponential probability distribution looks similar to this. And what this question is asking us is, what is the probability that we are somewhere between 6 and 9 days? Now, when working with an exponential probability distribution, I recommend that students always set their problems up like this. The probability that S is less than or equal to S less than or equal, the probability that S is less than or equal to X less than or equal to T will always give you the right answer, and it will help you solve some challenging problems um, later on. So what we have here then is S and T, and we're saying that X is somewhere within this region, right? Importantly, we have a limit here that X must be greater than or equal to 0, and our lambda must be greater than 0. So our rate must be greater than 0, and our time must be greater than or equal to 0, right? Meaning that time cannot be negative. So in this case, what is the probability that it will occur between 6 and 9 days? So this is saying the probability that S is less than or equal to X less than or equal to T. Well, this is equal to e to the power of negative lambda times S minus e to the power of negative lambda times T. So we go ahead and we punch these values into our calculator, and that's exactly what we get. So 0.5488 minus 0.4066 gives us 0.1422. Okay, if you set up your equation like this, that is this equation right here, for exponential distributions, everything will make sense and will be a lot easier to solve as long as you set your problems up like that. Okay, give me 1 second. I'm just going to pause my sharing, and I am going to go to another challenging question for you. And let's look at this question right here. So I'll give you a few minutes to try it on your own, and then we will do it together. Or before we do this, are there particular questions that you want, or do you just want challenging questions in general? Okay, sure. I'll give you a few minutes on this question. Okay, so Baffin Bay, located between Canada and Greenland, is being explored for oil and natural gas. First, an energy company conducts a geological survey, and if the data looks promising, it starts drilling. A recent survey of one area cost $65 million and indicates that drilling would be successful with a probability of 0.21. Drilling costs $0.32 billion with a probability of 0.7 and $0.65 billion with a probability of 0.3 due to the fact that the survey does not identify geological structures precisely. In other words, it may be easier or harder to drill through the rock. And that will inform our drilling cost. If drilling is successful, the revenue from the sale of oil and gas will be $2.7 billion with a probability of 0.75 and $0.32 billion with a probability of 0.25 due to uncertainty about the future prices at which the company can sell the oil and gas. Okay, that makes sense. Oil and gas isn't a static price. It's dynamic, so they don't know exactly how much they'll make, but they can forecast it with some probabilities. So what is the expected cost of drilling in billions of dollars? Well, all we're going to do here is count our expected value. So the expected value of X is equal to the observed value of X multiplied by the corresponding probability of X. So this is relatively straightforward. So $0.32 billion times its corresponding probability of 0.7 plus 0.65 billion times the corresponding probability of 0.3. This gives us an expected drilling cost of $0.419 billion. We're then asked, what is the standard deviation of the drilling cost in billions of dollars? Well, first we're going to go ahead and calculate our variance. So our variance is equal to the sum of the observed value of X minus the expected value of X squared times the corresponding probability of X. So 0.32 billion minus 0.419 billion squared times the probability that that event occurs, which is 0.7, plus 0.65 billion minus 0.419 billion, that's what we calculated in A, squared times 0.3. This will give us a variance of our drill cost. This is going to be in billions of dollars squared, which doesn't make a lot of sense, but we'll take the square root then of the variance, and we'll get a standard deviation of our drill cost to be 0.1512 billion dollars. We're then asked, what is the expected revenue in billions of dollars? And in this instance, we have to remember that the survey has said that there is only a 21% chance that we actually are successful. So just 2.7 billion times the probability that we can make 2.7 billion, 0.75 times 0.21 plus 3.2 billion times 0.25 times 0.21. You could factor out the 0.21 if you wanted and just multiply that sum by 0.21. It will give you the same answer. But your expected revenue then is $0.59325 billion. The trick in this problem, in this question, then being that you have to account for that there's only a 21% chance that you're actually going to get any oil in the first place. So that would be the trick that most people would probably forget to factor that into the equation. And then finally, what is the expected profit in billions of dollars? Well, the next trick in this question is actually that as business students, we know that profit is revenue minus cost. And yes, you did calculate the expected drill cost up here in question A, but what this did not include was the cost of surveying that was given to us in our question. And we have to account for that in our profit. So really we have to calculate then an expected cost, which is just the drill cost plus the drill cost plus the survey cost. So this is 0.419 billion plus 0.065 billion. This is converting the millions of dollars into billions of dollars so that we keep our units consistent. So our expected cost then is $0.484 billion. And then we can calculate our expected profit to be $0.10925 billion. So definitely a couple little tricks on that question. Nothing that's overly challenging, but it would inevitably trip a number of students up. So we only have 4 minutes left. So what I'm going to do is I'm going to stop recording. So thank you for watching.